Hello and welcome to this video lesson on standard electrode potentials. And the clue about the subject for this lesson is in the word standard, as in standard conditions, because redox reactions are equilibrium reactions, of course, and as you'll remember from the topic on equilibrium, the equilibrium position changes depending on things like concentration and pressure and temperature. And so if we want to compare different electrodes to each other, then we need to measure them under standard conditions. So that's what this video lesson is all about, and it has specification reference 3.5.3. So our learning objectives for this video lesson are, firstly, to understand how cells are used to measure electrode potentials by reference to the standard hydrogen electrode. So using the standard hydrogen electrode to measure electrode potentials of various other half cells, and so that we can compare them to each other. And secondly, we need to know the importance of the conditions when measuring the electrode potential, and we need to know what the standard conditions actually are, what temperature, what pressure, what concentration make up these standard conditions. So that's what we're going to do in this video lesson. Let's start. Yes, let's start with the standard hydrogen electrode. So you'll remember when we're doing relative atomic masses, we compare everything to carbon-12 isotope. Well, it's sort of similar here in electrode potentials, where we compare everything to hydrogen and a particular setup of a hydrogen electrode. So what we do is we say that the hydrogen electrode potential is 0, and so anything that oxidizes versus hydrogen is going to have a negative electrode potential, and anything that reduces when hydrogen is the other electrode, then that's going to have a positive electrode potential. And the scale of that difference between the hydrogen and the other electrode is a recognition of the reactivity of that electrode. Okay, so here we have a diagram of a standard hydrogen electrode, and let me point out some important features about it. So firstly, let's have a look at the setup here. What we've got is we've got a sort of upturned test tube with a side arm here, and through the side arm we were going to pump hydrogen gas. So H2 gas is going to be pumped in, and the first thing to note is that the pressure, the standard pressure, is 100 kilopascals. So let's write that down there. 100 kilopascals is the standard pressure, so it's pumped in at 100 kilopascals, and what happens, it bubbles into a solution of hydrogen ions, and the hydrogen ions and any other solution needs to be 1.00 mole per decimeter cubed concentration. So that's another standard condition. 1.00 mole per decimeter cubed is the concentration of any solution you use, and the temperature that it needs to be at is 298 Kelvin, which is about 25 degrees, which is 25 degrees Celsius. Okay, what happens is the hydrogen gas comes past a platinum electrode. So this platinum electrode, it's actually foil, and the only reason it's foil is because platinum is very expensive, and to use a big chunk of platinum would be expensive, and so foil is just as good if you've got the same amount of surface area. So what happens is that the hydrogen gas and the hydrogen ions do their reacting on the surface of this platinum electrode here. So either you're going to get reduction or oxidation of hydrogen and hydrogen ions, and whether it is oxidation or reduction depends, of course, on the other cell, and we'll come to that in a second. But first, just let me reiterate the reason why we use platinum as in the standard hydrogen electrode, and that is because, of course, you can't have a gas electrode. You need a solid electrode, and it needs to be able to conduct electricity, and it also needs to be inert. It doesn't need to take part in the reaction, and so consequently platinum is a very good choice, and that's used in the standard hydrogen electrode. So, and I just want to remind everyone of the standard conditions. We've got 100 kilopascals pressure of any gases. We've got 298 Kelvin that the reactions are conducted under, and we've got any concentrations of solution. In this case, we've got hydrogen ions. It needs to be 1 molar concentration. So let's measure some standard electrode potentials, or at least one anyway. But first, let's remember that the standard electrode potential of a half cell is the voltage measured under standard conditions when the half cell is connected to a standard hydrogen electrode. Okay, so let's connect a zinc half cell to a standard hydrogen electrode. So you'll recognize on the left-hand side of this diagram, you'll recognize that as the standard hydrogen electrode from the previous slide. And on the right-hand side is the zinc half cell that you'll recognize from the zinc copper electrolytic cell that we did. So just to be clear, what we're going to do here is we're going to measure the standard electrode potential of zinc, of the zinc half cell. And firstly, let me just point out that the two solutions, there's a zinc solution here, that's 1 molar, and the hydrogen solution in the standard hydrogen cell is also 1 molar. And you notice that the pressure that the hydrogen is being pumped in at is 100 kilopascals. So we've got standard pressure and standard concentrations, and we're doing this at 298 Kelvin, so the temperature, standard temperature as well. So firstly, let's write down the standard representation of this this cell. And you notice on the left we have the standard hydrogen electrode with the platinum electrode, and that's a solid. So we need a solid vertical line between that and the hydrogen gas. And the hydrogen gas, our oxidation reaction is the one we put on the left, and then we put the reactant first and the product second. So hydrogen gas oxidizes into hydrogen ions. So we write on the left hand side we've got the oxidation reaction, you remember. So hydrogen gas to hydrogen ions in different phases. So we're going to put a vertical line between the reactant and the product. Then of course we've got the salt bridge, 2 vertical lines, and then we're going to write down the reduction reaction from the right hand side half cell. So the reduction reaction, the reactant would be zinc ions, zinc 2+ ions, and they're in solution. And we need a solid line because the product of the reduction reaction is zinc solid in a different phase. We've got a solid electrode and aqueous ions, so we need a vertical line there, and that completes the standard representation of this cell. And in fact, on the left hand side, when you're measuring standard electrode potentials, this standard hydrogen electrode is always how it would be written. So you remember from a previous video lesson that we said that the one with the most negative electrode potential goes on the left, but there is an exception to that rule there, and that is with the standard hydrogen electrode. We always write the standard hydrogen electrode on the left by convention. which means that, and that's what results in either negative electrode potentials or positive electrode potentials. All right, so if compared to hydrogen, then something is going to oxidize, then it's going to be a negative electrode potential, whereas if the other half cell reduces, then you're going to have a positive electrode potential, and it all depends on whether the other half cell is more or less electronegative than hydrogen. Anyway, that's the rule, and that's the exception to the rule. So next, let's write down the equation for the cell potential. So for the whole cell, we've got the electrode potential, and we're under standard conditions, and we're working it out for the whole cell. And so that is going to be, you'll remember, the electrode potential of the right-hand side. We're still under standard conditions, and we're going to subtract from that the electrode potential of the left-hand side. Okay, and we've already said that the left-hand side, which is the standard hydrogen electrode, is by definition 0 volts. Is by definition 0 volts. That's just because scientists have said it is, and by doing that, it allows everything to be referenced against that. And then what we can do is we can look at the voltage meter here, because what this will gives us a cell, but as it happens, that equals the electric potential of the right hand side. Okay, so when we set the equipment up like this, and because we define the hydrogen electrode as 0, then the voltage reading it does give you the electrode potential of, in this case, zinc, the zinc half cell, and that reading could be positive or negative depending on which way the electrons flow. Sorry, before I move on, let me just correct a mistake that I've made. I think I said it correctly verbally, but I've written down E cell when I should have written down E left-hand side. Yes, is the E left-hand side, the standard hydrogen electrode is 0 voltage. Sorry about that. And lastly, as usual, let's just check we've covered off our learning objectives. First one of which was we wanted to understand how cells are used to measure electrode potentials by reference to the standard hydrogen electrode. So we spent a slide looking at the standard hydrogen electrode, and we measured the zinc half cell against the standard hydrogen electrode. And before that, we actually mentioned the importance of the conditions when measuring the electrode potential, because we've got equilibrium reactions, and whenever we've got equilibrium reactions, Le Chatelier's principle holds, which says that the equilibrium position is affected by things like temperature, pressure, and concentration. So then we went through and we listed out the standard conditions, whereby temperature was 298 Kelvin, and we had pressure was 100 kilopascals, and we had concentration was 1 mole per decimeter cubed. They were the standard conditions, which you now know. So I think we can say that those learning objectives have been covered off. Thanks for listening. Hope that's clear. I'll see you in the next video lesson.